Assalamualaikum warahmatullahi wabarakatuh. Today, our group will be presenting our project on enhancing the performance of a vapor compression refrigeration system. Assalamualaikum. Before we begin, let me first introduce the group members. Firstly, myself. My name is Muhammad Faizal bin Muhammad Rafi. And then we have Muhammad Nur Shahid bin Nazri. And then we also have one Muhammad Adib bin Wan Shuhaimi. Now, basically, refrigeration and HVAC systems are critical to modern industries, but they represent a massive global energy footprint, accounting for roughly 15 to 20% of total electric energy consumption worldwide. So, this makes improving system efficiency an absolute priority for engineering sustainability. And in our studies, we focuses on a baseline single-stage cycle operating with R134A as the working fluid. Currently, this baseline system operates at a critically low COP of just 2.5. And from an engineering perspective, this means that for every kilowatt of power given to the compressor, only 2.5 kilowatts of heat are removed. This low efficiency stems from severe thermodynamic irreversibilities during throttling and single-stage compression, resulting in high operational costs and excessive grid power consumption. Furthermore, there is regulatory urgency. While R134A has zero ozone depletion potential, it carries a high global warming potential of 1,430. Under international frameworks like the Kigali Amendment, we must face down high GWP fluids. Rather than opting for an expensive complete system overhaul, our project takes the most economic route, optimizing the internal cycle architecture to reduce power draw, thereby lowering indirect greenhouse gas emissions at the source. Now, Therefore, our project sets out to achieve three core objectives. Firstly, we aim to redesign the baseline architecture using advanced concepts like multi-stage compression and flash economizers to boost the COP to a target of at least 4.0, representing a minimum of 60% efficiency improvement. Secondly, we will perform rigorous manual thermodynamic calculations to mathematically verify our theoretical gains. And finally, we will validate these analytical calculations against continuous real-time models using fly carpet simulation software. So, with that established, let's look at our design.
Assalamualaikum to Dr. Azahari. My name is Wan Muhammad Adib bin Washwaimi and my metric number is DD240045. For the design section, I will explain the baseline system and the proposed system that we designed to improve the refrigeration performance. The baseline system is a basic single-stage vapor compression refrigeration cycle using R134 refrigerant. It consists of four main components, which are the compressor, condenser, expansion valve, and the evaporator. The refrigerant is compressed by the compressor, release heat in the condenser, expand through the expansion valve, and absorb heat in the evaporator before repeating the cycle. Although this system is simple and commonly used, it has several disadvantages. The compressor has to work harder because all compression happens in a single stage. In addition, the expansion process causes energy losses due to throttling. As a result, the system only achieves a COP of about 2.56. To improve the performance, we redesigned the system into a two-stage compression cycle with a flash chamber economizer. The main difference is that the compression process is divided into two stages instead of one. A flash chamber is added between the compressors. This component separates part of the refrigerant into vapor and liquid. The vapor is used to cool the refrigerant between the two compressors, which reduce the work required by the high-pressure compressor. At the same time, the liquid refrigerant becomes subcooled before entering the expansion valve. This increases the cooling effect inside the evaporator. For the design improvement, the compressor uses less energy while the evaporator provides more cooling. This combination significantly improves the system efficiently. The COP increased from 2.56 in the baseline system to 4.54 in the proposed system, which is about 77% improvement. Therefore, the proposed design successfully achieved the project target of a COP greater than 4.0.
Assalamualaikum to Dr. Azahari. My name is Muhammad Nushaib bin Nazri. My matrix number is CD240106, and now I'll show you our calculation that validate our design. We analyze both the baseline and our purpose system using a cooling capacity of 1 kilowatt operating between -10 and 40 degrees Celsius. For the baseline state system, our hand calculation show a refrigerant effects of 136.25 kilojoules per kilogram and compressor work of 53.17 kilojoules per kilogram. This gives us a baseline COP of 2.56 when compared to the fly carpet simulation value of 2.539. We have a very minor error margin of only 0.82%, validating our baseline model. Assalamualaikum. For our proposed two-stage system with an economizer, we introduce an intermediate pressure of 0.45 megapascal. Due to the flash separation, the vapor fraction is 15.4%. The total power input for both the low pressure and high pressure compressor is reduced to just 0.22 kilowatts. This result is a calculated COP of 4.54, which is a massive 77.3% improvement. The simulation yields a COP of 4.01, meaning both methods successfully crossed our project target of 4.0. For our moving on to the discussion, two main thermodynamic mechanisms drive this performance jump. First, the intercooling effect, which cools the superheated gas between the compression stage, significantly lowering the compressor work. Second, the subcooling effect, which shifts our evaporator inlet state to the left, drastically reducing flash gas and increasing our net cooling capacity. We did observe a 13.1% discrepancy between our manual COP and the simulation. This is entirely acceptable and is caused by manual rounding during double linear interpolation, whereas fly carpet uses continuous real-time NIST equations. In summary, both our analytical and simulated result prove that these two stages modification successfully meets and exceed our performance goals. Thank you. Moving on to the
Now, to wrap up our presentation, we have demonstrated that implementing a two-stage cycle with a flash economizer successfully overcomes the strict thermodynamic limits of traditional single-stage systems. This architectural modification delivers a substantial reduction in throttling losses and compressor workload. Importantly, our projected performance gains and ambitious COP targets were fully validated by both our rigorous mathematical calculations and also our real-time computer simulations. The alignment between these two methods confirms that the theoretical efficiency is entirely achievable in a practical setup. Ultimately, this redesigned system offers a practical, highly efficient, and exceptionally cost-effective pathway for green industrial refrigeration. It bridges the gap between economic viability and also environmental sustainability. So that's all. Thank you for your time.